So, good afternoon. I know being the first, there are some advantages and some disadvantages. We don't have a reference point, how to, what is the expectation, and where to start, where to stop, and all these things. So, we have been working on this particular area for almost maybe close to a decade, and a couple of students, a couple of PhD scholars have worked with me on these topics. And as Vice Chancellor suggested that I tried to be, as far as practicable, I tried to be non-technical, but it's very difficult to be non-technical actually for a technical person. So before I start, I would like to acknowledge, because before I forget, so Mini is one of my PhD students. Couple of students who are my master students in the last 5 years. Couple of them are now pursuing their PhD in the United States, like Deepak Kose is pursuing his PhD in State University of New York. Nityanand worked with us as a ILSA student fellow for some time, and of course Dr. Samrat Sawat from School of Physics. Half of the work belongs to him. And we also like to acknowledge the Department of Science and Technology for the funding for these type of researches. I mean, these are standard Wikipedia definitions, but just for completion, we need to talk about what's a sensor. So a sensor, I mean, mostly people understand it, but the most correct definition of this is that there are two ways of looking at it. One is that it's a measure, like it gives a measure of some physical quantity and converts it to some signal. So when it comes as a signal, and then we have the rest of the things in place that we take care of the signal, convert it to digital, and what we do with that. It is not necessarily that every sensor gives us a signal. There are some sensors which gives us not necessarily signal, but we need to have something else to convert it to a signal. Say for example, we have in a couple of slides later I will show you some applications where we work with water quality also. So all water quality sensors does not give me necessarily signals, but we need to design some other mechanism to convert that to a signal. So a sensor is a converter that measures physical quantities and converts it into signal which can be read by some instrument. And these days, no other instrument is required. Any electronic instrument is good enough to read these signals. And the other definition it says that a sensor is a device which responds to an input quantity by generating a function-related output. This is a slightly more comprehensive, because the moment you take an input, when the input varies, the output has to vary also. So then we measure what is that input and what is that output. And that's one of the criteria when we purchase a sensor or when we go for a sensor, what is that range that it can detect? For example, if I go for a temperature sensor, can it measure temperature of a blast furnace, or it is meant to measure the temperature of a human body? So that range is different. So depending on the range also you have to select the sensor. Going down to the next part, what's a network here? So again, referring back to Wikipedia, so a wireless sensor network is a spatially distributed, I would like to highlight some of the words here. Autonomous. They are basically autonomous. It's a purely distributed environment. Nothing centralized about it, but we try to make it centralized to by some means or other. So it's an autonomous sensor to monitor the physical and environmental conditions. So when I say physical, we talk about all physical parameters. When we say environment, we talk about humidity, we talk about temperature, we talk about pressure, we talk about what parameters, maybe the gas, what kind of gas we have, and all this stuff. Now I changed I think somewhere I gave a talk few months back, and there was a lady picture in that sensor network collecting the data. And somebody has a funny idea, why a lady collecting the data? I say, fine, why a lady? There's no lady there. So the lady is removed from here in this picture. So, so this is, it started long back, like in that DARPA, I mean, they are leading network companies. Way back in 1980, people started thinking about this kind of sensors and all these things. Quickly coming down to I'm just setting the field actually. So we have the component of a sensor, it's a block diagram. What it has, so I'm trying to differentiate between two things here. One is what's the node and what's the sensor. A sensor is just a measuring device. It just measures, converts into a signal form. What's the node? It consisting of all these things. It consists of sensing units, that means which can measure or sense data. It consists of a small processor, we call it a tiny processor. It has a database which can store it, we call it a tiny disk, everything is small here. It has a transceiver unit, because anyway it has to send the data, so we have a transceiver unit there which can transmit as well as receive data. It has a battery, because anyway it has to be placed in a place where we cannot have infinite power supply to that. So we have a battery, small battery, whatever type of battery, there are different types of battery, I'm not going to into that. So these are basically the 5 units of a sensor node. And the bottom one gives a, this one gives a kind of a picture, how it looks like. This is still a complete overview of these things. It says that, look, in one board, we have different sensors like humidity sensor, temperature sensor, 3D acceleration, 3 dimension in X, Y, Z, how it changes. We have light sensor, light intensity. There are other uses of the light also. This light sensor can be used to detect color when it comes to, when a colored object comes in front of it, it can detect the color also, whether it's red, green, blue, yellow, like that. It has a temperature sensor, but it depends on the range, as I said, that whether it's a temperature which can, at what range it works. So we have to look at the comparison there. We have a ADC, that analog to digital converter. Now in this board actually, we have some possibility of connecting external sensors, which are not part of, I mean, they are not humidity, they are not acceleration, they are not temperature, but still we have some other sensor developed by some science lab or somewhere, where some signal comes out, so we can connect them through this external connector to this particular port. Now that particular port works on a particular frequency. It doesn't work all these things. So we need to do something here, something at this point, at this point, so that external sensors can be connected to this node also if required. And this is our node program interface, like we write programs and the programs gets executed.
So this is for you, this is your particular sensor, but what you're telling us earlier was very general, right?
Complete general.
Right.
So
this is not particularly general, right?
This is not particular general. We take a sensor, and there are some external interfaces. So what we have done is that our node consisting of these external sensors, I mean, thanks to Dr. Sabat who provided me that interface, that how to connect it there, and then we designed that full body.
Because you can put any number of
sensors.
fields,
Yeah.
right? So this is basically something which is sensing different fields.
This is something. Yeah. This is sensing
Just go
different.
back one slide, please. If I want to think about it, you are collecting data on humidity, temperature.
This is on board. This is
I
what
know, but it need not have been, right?
did not happen. So this ITS 400 board, I mean, that board consists of this. Apart from that, we can talk about something else. Some of the challenges what we have is
just one thing. I mean, I think that for lectures like this, we don't have to wait till the end to ask questions and stuff. So please just break out and.
yeah. So some of the challenges, of course, because there is a generation change. In fact, that law also says that every 2 years the computing power, or every 18 months to be Moore's law, every 18 months to 2 years the computing power and other things doubles up. Of course, it has become saturated these days. And there is another law which says that every 10 years the computing paradigm changes. Now we have moved from small, then big, and suddenly we made a complete loop and came back to the smallest part of this. So these sensors are basically small, as small as possible. They're basically small. So size is important, form factor is important. Usually the numbers, when we talk about network or we talk about computer nodes, we talk about 4, 8, 16, 24, etc. Here we talk in terms of thousands. We talk about differences. I mean, they are not tied up to any location. They are not tied up to any particular point of attachment or point of connectivity, etc. They are low cost. They have to be low cost. In fact, sometimes the cost can be as low as few hundred rupees. And because of this low cost and other things, they are not very reliable. They are not very robust. They cannot be dependable. Anybody can replace them. So there are many challenges that happens here. So cost is an issue, but with cost comes the energy. So if you buy a sensor node which cost me $1,000, that doesn't provide me an energy which lasts for 1 year. So how do I do that? How do I manage that? It is an ad hoc deployment. We deploy it for a particular purpose, and then the job is done. We come back with that. So we need to talk about like what kind of network lifetime that this node can have, this network can provide, given this kind of algorithm, or given this kind of computations, or given these kind of applications. We come back to this. I mean, this is just a slide to say that there are various types of sensors available. I mean, some are available in India, some are available in the lab, some are available in commercialized form of this we call the off-the-shelf technology. And some are, yes, some are with us also, like we connect them actually. So we have electromagnetic sensors, we have mechanical sensors, we have chemical sensors, we have biological sensors, we have these pathogens and all these things I didn't list out here, but pathogens also, we have sensors for that. But maybe some of them are not available off the shelf. I cannot go to Secunderabad market and buy it, but they are there. They are there in some form or other. Depending on the application, we pick and choose, and these things are not compatible. That interoperability, that compatibility is an issue, but yes, we have to have a design where this compatibility can be taken care of. So we have these photo sensors, we have RF, we have ECG, EMG. I mean, these days actually, I need to take a few seconds more here. These days, it need not be a sensor which is available. For example, if somebody asked me, I think few days back, do you have a sensor to measure stress? Well, I don't have a sensor directly to measure a stress. But what I have is that I have a couple of other sensors which can be put together, and I take these multiple parameters, write an algorithm for that, do a case study for that, write a machine learning algorithm for that, and that system, that integrated system can measure stress. But we don't have a sensor which exactly measures stress. There are some companies which say that we measure stress, but they are not the case actually. So we go down to what is that sensor data that's coming up actually. The sensor data that comes up, there are two ways of looking at it. One is that accuracy and other is that volume. So that accuracy comes in two ways actually. How many samples, how many measurements I can make per second or per 2 seconds or per unit of time. And then each sample consists of how many bits, what is the size of the data. So this is a challenge actually. We have different sensors which have the sampling are different, and we have different sensors where the number of bits it samples is also different. So the volume, the size, the packet length, so we talk in terms of TCP IP and all these things. That doesn't go well here. I mean, it doesn't suit into that particular formatting here. So then we have to decide what is the bandwidth requirement we have, and we know all these things are small, all these things are very less battery powered, and what is the bandwidth requirement, what kind of storage you need to have, and all those things comes in. This is how any sensing technology develops actually over a period of time. We first start with the principle. I can give you one example. For example, the sensor, the temperature sensors, gives me 10 samples per second. I mean, it depends on that. And the pH sample, that water quality, it gives me one sample in 10 seconds.
So what is the basis for finding the sampling?
The time required to measure that particular reaction. So if it's a chemical reaction, it takes quite a bit of time. If it's an electronic reaction, it's very, very fast. So it depends on what type of sensor it is, and that decides on how many samples you can have per second or per unit time, and then you move on. So this is how we have this growth. So we start with a principle. Some principle has to come from some science lab, and then based on that, people work with experiment. They do that experimentation and other things, and when they come up to a particular level, then we go to a design technique. Now this design technique actually, if it has to be a sensor, it has to be a particular form factor. That form factor is also important. Then we talk about miniaturization, and slowly we get into the energy issues. Because if it has to be used as a sensor, then we have to consider how much energy it consumes and all these things. Then it becomes a sensor, and finally it goes into a node. So this life cycle of a particular packaging kind of thing, it goes into a node. This entire life cycle starts from this small physics principle, chemistry principle, biological principle, or some principle, and then slowly it goes into a sensor node. This life cycle has to be completely completed. So just to give an example, how it started with because this is the accelerometer sensor, which is almost omnipresent. It presents everywhere. I think in this hall at least 50 or 60 accelerometer sensors will be present because they are part of the mobile phones. So how it started way back in 1923 in some lab actually. I may not be well versed with all these technology, but I'm just showing here how the evolution happened and how it moves from one. So sensors were not there in 1923 because the form factor was not available. This piezoelectricity came in 1943, piezoresistivity came in 1959, Hall effect. And when people started using accelerometer, using this Hall effect, then they started using it as a kind of a measuring device. Until then, they were not using it as a measuring device. Now, if you go down, right now, the mobile phones, what you have is basically MEMS space. So these MEMS space sensors are basically very, very small, very, very thin, very, very can go into my mobile phone. But until then, it was not being used. If I go to this pulse oximetry, because this is another one which I want to say. If I go into the pulse oximetry, like I need to measure the oxygen content in my blood and other things. There are probes available, there are sensors available, But again, the accelerometer sensor, I mean the number of samples, there is an accelerometer which you see here is giving me 100 samples per second. But pulse oximeter doesn't give me 100 samples per second. It takes quite a bit of time. How it works, the pulse oximetry can be used to measure oxygen content in my blood. It can also be used to measure to some extent heart rate. I mean at what rate my heart beats and all these things. So if I look at this, they use a kind of a light and what is the absorption amount, and based on that absorption amount, they calculate what is that is left, and how it is used for heart rate also, because when you start, when the veins, when the blood flows there, so there is a pressure changes, and when the pressure changes, the light intensity also changes, and based on that they measure what is the oxygen content in the blood. Now what I am saying here is that it's not about that how the pulse oximetry works, or I am not going to explain here, but I am saying that there is a principle, and from the principle there is a device, there is a design factor, and from the design factor people come up to a particular form factor, and then it is tested as a sensor, and then if it has to go to a sensor node, it has to pass all these parameters like how do I interface with the existing sensor node, what is the standard, do I need to design another circuit for that, do I write to some algorithm for that, and that's how we work. We also have ECG, and there are many other things actually. In fact, I just wanted to highlight a couple of things here because I just want to say that okay, some principle is there, and from that principle they pick up a device, and that device slowly gets miniaturized by using of MEMS technology or nanotechnology or some technology. Even this couple of one sensor I didn't write it here, but I'd like to tell that the graphene. So graphene, this image sensing in graphene. After this graphene came into existence, this is research. Now all these image sensors are being replaced by the graphene. Now graphene says that you don't need a class. You don't need a class if you are using a graphene material for that. And probably in a couple of years' time, you will see that the graphene also comes into the image sensing. So these are the things like I have the last line, the last paragraph if you read, the ECG signal is small actually. That's what I wanted to say, that all these things are not same. They are not same in terms of the voltage output. They are not same in terms of the sampling rate. They are not same in terms of the size of data that generate. So everything is different. But ultimately, you have to build up a system which includes everything. So we have a sensor here on which if you put your finger, so that kind of that heartbeat, right? And here it will start beating here. When you can see the pulse here, and based on that they calculate. And now, I think a week back only I saw one was, now they are saying that the heartbeat can be measured even from a distance of 7 feet. So that you really need not come closer to this actually. And I think there is an interesting slide there also. So it can even be measured from a distance of 7 feet. So you don't need to really come closer to me to know what is my heartbeat actually. Okay, so the world is full of sensors, as I'm trying to say, that there are already many sensors deployed, and you have cell phones already deployed with sensors. We have surveillance cameras, they are sensors. We have GPS, they are sensors. We have motions, light sensors, many more. You talk about anything, almost sensor is available. Now, the thing is that now let's connect them to a network. So that's where we said that it's a network of sensors. So sensors are available. Now if I connect them, now it becomes a network. Now so far the sensor network research is that I connect it to a network, connected to a base station, and I don't care beyond that. I don't care beyond that. At base station they say that it's provided with infinite amount of power, server is there, it is always there. So you don't worry about what happens to your data in the base station, and base station is always ready, available and other things. But you ask me how much time in Indian context or in any context, how much effort and time is required to make any system 24/7 available. We have that problem everywhere actually because of this power situation and everything. So it's not true that we don't have to consider beyond base station. We have to consider beyond base station. Now if all this sensor data somehow goes beyond base station and connected to internet, then it leads to another term called Internet of Things. Like you have everything there, and then this comes how to retrieve, what is the structure of this data, how do I index them, what do I do with that data, what is the and all those issues comes up there. So the factors influencing, by the way, I have already told what are the different factors here. Scalability, yes, it's an issue. I cannot design a distributed system for 10 nodes, 20 nodes, 30 nodes. If I think of a distributed system here, I have to think of a distributed system of 1,000 nodes, 2,000 nodes, 5,000 nodes, like that. As I said, that the fault tolerant, they are supposed to be placed outside. They are supposed to be cheap. They are not very reliable. They are not very robust. Fault is an integral part of. I cannot assume that my node will not fail. So that assumption is a very, very hard assumption to make. So it is there. How do I do that? What are the Harvard constraints? I've already said that everything is tiny here, everything is small here. What is the topology? We don't have a topology like mesh topology, tree topology, this standard topologies, what is read in network, they don't work here. Environment, security is an issue because they are deployed outside. You cannot have a security guard meant for a particular sensor node. You have some few thousands of rupees per a node. You cannot have a security guard there. How do I trust the data that is coming from this sensor? So all these issues are there. And of course, power consumption issues are there. This is a architecture we have been living with it for last almost 5 years, and we have been whatever applications we develop, somehow or other we refer back to this architecture, and it talks more of almost all areas of computer science. It also talks about electronics. It also talks about many other things. Now, if I look at the upper part of the diagram, we have a sensor probe 1. Very carefully, we chose the word sensor probe because the probe here is anything that gives me some data. And that calibration block there, calibration circuit block, is basically to make it compatible to the sensor which I am using. I might be using different types of sensors. Then it comes to the sensor board. The sensor board has a processor in that also. It also comes to the processor board. So what is the processor board? It can do some kind of a computation. Although it is tiny, but still it can do a bit of computation. And then you have a transceiver which can transmit the data. So that makes one particular node, let's say S1. I don't know what kind of sensing it is, whatever sensing it is, but that makes a node S1. So we have something like S1, S2, S3, S4 up to Sn. There are n number of nodes. And each number of node, it will keep on collecting data, whether you want it or you don't want it. So we write a algorithm, we write something which is called a DF, stands for data filtering here. So we filter the data. Some of the data we don't need. So for example, as I told, the temperature sensor will collect 10 samples per second. What I do with all these 10 samples per second? I don't need them. And I only collect them, store them in a time frame. I say that from this time to this time, this is the temperature. Other time, if there is no change, I don't record them. And it doesn't change unless there is some exigency, some emergency, it doesn't change. So we have data filtering algorithm there. And now, what is the data aggregation? DS stands for data aggregation. It's a distributed algorithm. But how do I look at that? Suppose in this room there are 10 sensors placed. What is the temperature of this room? Who will report? Who will say? And they are autonomous agents. They are distributed. Who takes charge? Who delivers that? What is the temperature of this room? If it is averaging, who does that averaging? So all these things need to be addressed. Leader election algorithm we talk about in distributed environment. So everything comes here. Now all these things comes and we get the data into the central data logger. So this block. This block talks about my database. It talks about my decision support system. It talks about my data abstraction. The data abstraction in data mining term and other things called data summarization, data summarizability, and all these issues comes here. Why I'm talking about all these things? Because ultimately, we have to take intelligent decisions to reduce the false alarms. That true acceptance rate has to be increased. The false acceptance rate has to be decreased. The false rejection rate has to be maximized, and true rejection rate has to be maximized. So, but these are the things which you cannot achieve in one go because they are conflicting objectives. And in case of conflicting objectives, we need to look at that. What is my priority? How do I model this problem? So all these things comes here. At the moment I detect some kind of an alarming, where this architecture we live for alarming event, we need to alert the users what is to be done. And once the alarm notification is done, and all these things said and done, but we don't know whether this alarm is a true alarm or not. That's number one. Whether this alarm which is applicable in Delhi, same alarm is applicable in Hyderabad or not. For example, when we are working with water quality, we said that the quality is a perception. The water which I can drink, maybe yesterday Elizabeth Kuchnan will not drink that water because for them quality is slightly different. So how do I model that? How do I model that perception as a quality? And if somebody says no, this is not the standard. This we cannot accept. And this is how we have this machine learning unit which learns these rules and tries to change the rules internally. And these rules it will learn over a period of time. Once you deploy it over a period of time, 1 year, 2 years down the line, it will learn its own rules, gets adapted to the system, gets adapted to the demographic also. So this is a general architecture which we lived with for quite some time here. This is what the major issues here. So we are basically concentrating on designing prototypes and how it can be used. So we have data acquisition model, we have data analytics and decision making, we have machine learning, we have communication protocol because the standard TCP/IP communication protocol doesn't work here. IEEE has a ZigBee standard, but ZigBee standard is not compatible to my mobile phones. ZigBee standard is not compatible to my server. How do I do that communication protocol? There are some communication protocol which we started using it, changing those parameters. And we also work on this mathematical models, because there is a term I'm using here, soft sensor. So the soft sensor is basically where this soft computing features come in there. I have a sensor. Say, for example, I'm saying that my heartbeat is, let's say, now slightly more. It's because of my anxiety or because I'm running. So if I'm right now also referring to a gym. While I'm doing a gym, my heartbeat will increase. But is it alarming? It is not alarming because now I'm in a gym, but I'm sleeping and my heartbeat is increasing. Is alarming? So I cannot have one sensor to say that this is alarming. I need to have multiple sensors. I need to correlate them, and then only I can come out with a option or come out with a final answer. Is it alarming or not? So this soft sensor is basically we are trying to replace some of the hard sensors, some of the physical sensors with soft computing techniques, with algorithms, with models, and that will have two aspects. One, it will replace a physical sensor, because if I know that, okay, if the temperature there is 25 degrees centigrade, there is an AC there, and AC is not here. If I can model it, that what will be the temperature here? Why should I have a physical temperature sensor here? That's what the idea is. The issues, the research issues that we are handling in each of these modules is that we have data acquisition. So there we have this physical sensor, sensor selection, synchronization. We need to synchronize them. We have data analytics and decision making, where we have signal processing algorithms and all these things. We have machine learning algorithms. For me, right now, I have not used everything here. I've just used one basic component of each unit, developed a prototype, and waiting for it to develop beyond a particular person. We have communication protocols. People have started using Zigbee. Now we are using DES7. So there are different protocols for sensor network standard, and that has to be corroborated with mobile protocols, with server protocols. We have a soft sensor, and this is presently we are concentrating on that. How do I replace physical sensors? Not all, but some, with some model, with some mathematics, some model. Because if I understand what is the chemistry, what is the physics, what is the biology behind those sensors, then can I replace it with a particular? So I have two here, and I can always interpolate what will the value here in between these two. If it is not that, if it is a pipeline, say, if it is a pipeline and I have to measure flow, I can measure flow at the one end, I can measure flow at the other end, and I can find out what is the flow rate in the middle if I can mathematically model it. I don't need a sensor. Okay, so and these are some of the issues here where I have a power and cost that has to be looked at. Reliability is an issue. Alarm is an issue. Actuator is basically reaction. If something happens, you need to react. Generating a bell is an actuator. Opening a gate is an actuator. Opening a switch is an actuator. So something like that. Basically, this is the complete system model, and I said that we have been living with it for a couple of years last. We have a data acquisition system where I talked about data conditioning, data filtering. We have a processing subsystem where we have talked about data aggregation. How do I aggregate data? Who is responsible for aggregating the data? We have a communication system where we have three models. Always communicate, doesn't matter what you sense, you communicate, but that's not a good model. Never communicate, wait for the server to ask you the data, then you communicate. That's also not a good model, because sometimes you need to send it. And then selectively communicate. You communicate only when you feel that it needs communication. There is some alarming event there. This is also, I mean, one student did it actually very well. One-way notification and two-way notification. If there is some alert, the alert comes to me. I mean, we integrated it with mobile phone, integrated with email and all these things. The alert comes to me in my mobile, but we don't believe always that no news is a good news. If nothing comes to me as an alert, it cannot be taken for granted that everything is fine there. So sometimes what we do is we have a two-way message. We send an SMS to that particular, I mean, we use GSM modem here. We send an SMS to that particular server. The server sends a signal or a communication to that particular sensor node, pulls the data, composes as an SMS, sends it back. And that's how, all these things are done in a passive mode, so that I don't need to actually disturb that particular person. So this has been implemented in fact. This is a snapshot of the, I mean, it's somewhere in 2011 or something, we started with that. So this side says that how the data is coming, just to give a snapshot. This is a bit of programming what the students have done. This is what we have, the user interface, to the SCI there, where you can have your, what kind of node, where it is deployed, and all these things are there, and you get the data there.
What is the data that you are collecting?
This data we started collecting accelerometer data, pH data, light data, and motion data. These are the 4 things we started collecting.
In some water.
In water we collected pH, dissolved oxygen, turbidity, salinity, and pH, DO, turbidity, salinity, ORP, oxidation reduction potential, ORP, Temperature is there, it is, by default it is there, but that is not specific to water quality. But ORP we have collected, so these are the data we have collected. This is a model where, say, for example, for each call we need to write a code actually. And we find that in that board, what are the external interfaces, what are the internal board, and if in that particular node we have these sensors. So just these are the radio buttons, we click the particular code or program that whatever has been written, that will be deployed in that particular node, and then it goes to, so, and what is that alarming? We first started with the threshold mechanism actually. So the threshold is that if it is within the range, it's fine. If it goes beyond the range, then you start an alarming. But that's not a good model. We tried with spatial gradient, we tried with temporal gradient, we tried with moving window average methods. So all these things basically we wanted to do it so that the alarm will not be false. Or as far as practicable, the false alarm rate can be reduced. This is what we did for a couple of years, and we will be doing it for another 2 years actually. The DSC gave us some money between 2008 to 11 to study this, and based on this actually, DET or DET gave us some more money to go ahead with that. So what is this objective actually? We need to design a wireless sensor network zone for drinking water quality monitoring system. These are the things actually. We have pH, DO, turbidity, salinity, conductivity, chloride, ORP, and also arsenic. That arsenic we didn't do, but we'll do it now. So what is our purpose actually? To develop an indigenous, intelligent, adaptive decision support system for online monitoring of the remote water quality. It's not, right now what is standard, you get the water, go to the lab, test it and do it. But when I was making this presentation to the program advisory committee or project advisory committee there in Delhi, they say that, look, we appreciate one of these aspects is that all these water bodies in India almost are unguarded. And what happens if some external agent is being put to that, and how do you take care of that? What is that we can do to that actually? So these are some of the things which you can say, okay, online, immediately if something happens, something goes wrong, we get an alert, we get an SMS or we get a mail, we get an alarm, what is to be done there? This is what is done almost. So we have these things like who should be contacted, where if it happened in University of Hyderabad, it should be contacted, some contact person will be there. If it happens in Gachibowli, some other contact person will be there. So that entire HCI, that human computer interface has been designed and it works. These are the, because we wanted to show a network, so this is part of the project actually. So again, thanks to Dr. Sabu that he finally came out within a box model. Because some algorithms, some models, some intelligent algorithms, everything goes into that, but it came in a box model. So these are the 4 things we can deploy it, test it. This one, because when we started deploying it, and we need to have a network and all these things. But the student who came to us with as an Insta student fellow or something, now we say that can we have a standalone system, no network. I don't have a network, it cannot come to this server and other things. Can I just put it in my override tag and start collecting data? And can it give me some alert and other things? So this is a completely standalone system. Everything is there, except much of intelligence is taken care at the server level, but all other things are there. The keyboard is there to configure it, which number is to be, message to be sent and all these things. It has a SIM in that. Well, it's an ethical issue, because whether we can use a SIM in this device, what is the proof of ID, what is the proof of residence there, and so all these issues are there, but we didn't bother about that at that point of time. So, so these are some of the results which we collected in the lab. Yeah.
How is the sensor powered? I mean, you are putting it in some remote place.
But
And if the battery runs out,
then it has to be changed. Then it has to be changed. So right, the next slide talks about that. So this is some of the lab results, how we tested. This is, sorry?
There are no energy harvesting solutions.
Right now, no. Right now, no energy harvesting, but the proposal what you have written now, Sabath has included solar cell, this energy harvesting and all these things, but right now, no. Yes. So, there are some of the interesting results here. Like we took the sample from a tap which is written as a drinking water, and the one which is normal take water. Not much of a difference. It's labeled drinking water, but it's not much of a difference. So, so some of the issues, as MGK pointed out, it's a power consumption issue. So we measured it, comes out to be 134 milliwatt, but yes, it doesn't. Even if I take my mobile battery, it doesn't last more than 7 days. Or if I'm slightly lucky, I'm not communicating too frequently, then it goes up to 15 days. That's an issue which we are still bothering. We have to look at that. Connectivity is an issue. and time synchronization. If there are multiple number of nodes, the server right now we didn't do is that at what time that MAC protocol, medium access control protocol, we didn't work at that. At what time the data will come, the server should be ready to receive the data and all these things. These are all wireless communication. So these are the things which we will be working in next couple of years. Some of these issues, by the way, I have already said, so this slide has no value. It has a sampling rate, it has observation error. All these sensors are not at all reliable. I mean, the right now what sensors we are using is, the data that comes is very, very unreliable. What do you do with that? How do I do with that? And particularly because there are physical, chemical properties are there, right? They are interacting between each other. What, I mean, I may be wrong with, but what we observed is that the pH value is particularly temperature dependent. So the same water at a particular temperature gives me one pH value and at another temperature gives me another pH value. That doesn't mean that it is not potable at two different points of time. So what you have to do is that, and this is true with body parameters and other things. So we need to correlate them, find out what is this value, and if this is the value, and what is the exact value. So that tabular form or that algorithm, that switch has to be made so that we give some 3-4 parameters, and this is the observed value, what should be the expected value or what is the exact value. So that is how we did all these things.
Can you just go back to the sensor, please? Where is the water?
No, this can be, okay.
Water goes into one of them?
No. So we have these points, right?
Yeah.
So here, because this has to touch. So here we connect it and touch it to it. I think I'll show you that we have okay.
It's not like you put this in a lake or something.
No, what we do is in that overhead tank, so we had a problem actually, we have to fit it actually. I think Kiran is here. He came out with a brilliant idea, asked the carpenter and designed a hand kind of thing, right? A floater. He took a floater and in that floater he just floated down and this hand is there actually. So when the water level goes down, the floater goes down. When the water level comes up, the floater comes up. So it ensures that this box, this always touches the water.
Not the box, the probe touches the water.
The probe, not this box. This probe.
Probe is connected to that.
Where's the probe? What is it doing?
Probe, okay.
So the probe you haven't shown.
Probe I have not seen. Okay. I think I have that picture somewhere. I didn't show it here, but I have that picture here. Okay. So this is something again we started experimenting with body array network. We lived with the same architecture, but what we changed here is that this central logging, instead of going into this server, I changed it to my mobile. So the data comes to my mobile. Architecture is same, everything is same. I just changed my database server here to my mobile phone. And what is this Blue Giga protocol? But as I mentioned, it didn't work. Like the sensors communicates with one protocol, mobile works with another protocol, so it didn't work. So we had to have a converter there. Blue Giga is like sensor comes, we use Bluetooth technology to send it. When Bluetooth comes, it comes as a SMS. When a SMS comes, it needs to be parsed and we put it in the database. So all these things are done, it works. So this is how it's Swami, this person is Swami here with this heartbeat sensor. So if you connect it and then, and this is the 75 and everything, it goes to the, but all this communication protocol, changing, connecting, calibration, everything goes behind it and finally it comes here. One interesting that happened, as I mentioned here, is that the accelerometer sensor gives me a good feedback actually, because this doesn't give me any information. Only heartbeat sensor doesn't give me any information, what is good, what is bad. But this accelerometer sensor actually, with that actually if you put, are you in sleeping position, are you running, are you driving, or what are you doing? And with that, if you put a SpO2, that pulse oximeter, right? So you know that at what state of mind you are. Are you running temperature? If you are running temperature, your heartbeat will be high. So all these things should be taken together, and then only you can conclude that whether it's alarming or not alarming. So we are doing something on that. This is the current and future projects what we have been working together for quite some time. The probe, water technology probe and everything, somehow or other it got listed among the 10 best projects by IBM. And then they contacted me what else we can do about it. So they have this IBM Smarter Planet project and other things. And it triggered like a couple of railway accidents, right, because of fire or everything. So it's not that it's not doable. Fire detection is there. So, but how do I place it in the railway coach? How do I detect it? What is the mechanism behind it? How do I send the data? Is it in place or not? So they wanted to do something. I think we are pitching in there and trying to find out that can we do something so that fire detection can be done. Interestingly, fire detection can be done. Like we have some, again, there is no sensor called fire detection. We have to take light, we have to take temperature, we have to take humidity, we have to take smoke. All these things taken together, we need to write some algorithm, and that will give me whether it's a fire or not a fire. And this is that Aqua 1 project is now changed to Aqua Sense project, where we want quantity, quality, everything. And there is a German company, the branch is there in Bombay, so they have shown some interest, but I don't know how far it will go. With JN2 Hyderabad, we are doing something called rescue management system. It's not very difficult, but probably people have not thought about it. Like we can have some sensors in the tourists. People are going to Amarnath, people are going to Vaishno Devi, people have gone to Badrinath, but what happened to them? How do I find them? How do I rescue them? So these are some of these. So I have something drunk and drive detection. The accelerometer sensor itself. I mean, we did some experimenting. The accelerometer sensor itself can find out the drunken driving by looking at how the vehicle turns. And how the vehicle turns actually. It's not that easy, because I may drive like this also, but it doesn't matter. Doesn't matter whether I'm drunk or not, but it gives me an alert, it gives me a beep, it gives me a signal to the police, they can come and check me. So epilepsy. In fact, I didn't do this work, but people have done it, epilepsy. The way you, suppose you are sleeping and you got an epilepsy attack, and again the accelerometer sensor there, your heartbeat, your pulse oximetry, your skin sensitivity, that skin conductivity. So all these things, if I have in place, then it can detect to some extent, it can detect if it is an epilepsy attack, and then you can send an SMS, you can send a doctor, you can generate an alarm and whatnot kind of thing. Old age home monitoring, it is there. I mean, I know a professor who has done a project in Taiwan, but nothing has been done in India. Let's see how it goes. So few more kind of things. So fire detection, I don't want to go for that, but
excuse me, sir.
Yeah.
So, are there sensors which are capable of detecting smell? Like one of the major problems in the domestic households is the leakage of gas and all. So, are there sensors which are capable of detecting them and reporting them? It would be.
See, it's a good thing that the sensors can detect smell. Yes, they can detect smell. But the sensor will also, the problem with India, I mean, one of the builder came to me and said that, look, our home is a smart home. What is that? You get into the toilet, you don't have to switch on your light, the toilet will be automatically illuminated, because it detects the motion and start detecting it. In India, what happens? You have lizards, you have cats, you have dogs, and everything will be detected, right? So, in here also, the smoke detector is there. But if the gas is open, it will detect. But even if it is not open, sometimes your burner is not working properly, it will detect that. So we need some kind of intelligence, filtering out. That's what I said, that it has to adapt to the demographic people. That it has to, so every time I don't like an alarm actually, right? And that's how I need to check it actually. So this fire detection, as I said, that we do it, mobile sensor based rescue management system, I mean, I'm part of it, I mean, we are part of it as an advisor, we are also doing it on our own. J2 people are doing it to some extent. And what you do here is that, and I said that thing, what actually happens actually in a rescue management system, the victim falls down, and then there is no way that the victim can communicate. Sometimes the victim can, so we've seen some of the apps, right? You press that and your location will go. But whether I'm under that GPS area, if I'm under a basement, etc., GPS doesn't work. And how do I do that? I mean, I cannot have a system where the GPS works, and whether the mobile network tower is working, they are not working. So how do I do it? Like, the sensors have to do that, and that's why I say that we have to have a localization algorithm, and we are also working on that, because all these things to happen, we need sensor network algorithm, we need sensor network CS research in that, and that's how we try to do that actually. So the victims in this case actually, so if I can find out, if I can put some sensor on a small device actually, maybe a mobile fine, but mobile doesn't work when the disaster happens. But if it is a small device, and if it can detect me that I am senseless, because I'm not at all moving for last 10 minutes, no accelerometer sensor detecting that, and then if it happens, can it send it? So, and what it sends? It sends, one is that it can send GPS parameter. Sometimes GPS is not possible, fine, it can send me a corresponding relative location from some devices. So that's what we try to plan it here. This is a block diagram. Yeah, I have done it. So this, so based on victim's respiration, heartbeat, and accelerometer, I'm again saying that all these three things should come together to find out what the condition of that particular victim, or what is the condition of that particular tourist that happened there, and then if it can alert the system to provide some help to the victim. CS research issues behind it actually. So to all these things to happen, right? For example, if I have to send my location, how do I know my location? That's where the sensor localization algorithm comes into picture. In the absence of a GPS. If I have to deploy in University of Hyderabad, let's say in whole of Hyderabad, if I have to deploy sensor nodes, where should I deploy? What is the critical area? How many sensors should be deployed? Because redundancy is required, because reliability is an issue. What is that? How do I do that? All these problems, we technically say that these are all hard problems. They are computationally hard problems, because there is no, I mean, the moment the area is more, the moment the number of sensors are more, they are exponential algorithms. I mean, we just cannot solve them in reasonably finite amount of time. And what algorithms we need to do so that the deployment algorithm can be used. What is that, as I said, what is the data aggregation algorithm? Say, I want to find out that there is some fire in that particular area. But in that particular area, there are 100 sensors. Who is detecting that? Who is coordinating that? Who is aggregating that? And remember, they are all autonomous agents. They are all distributed agents. They don't talk to each other much because there are energy issues. But somebody has to be elected as a leader through leader election algorithm. We have leader election algorithms. And then they start doing it. Routing algorithms are there. This is one, I mean, we worked on this security part of it, and we worked on zero knowledge protocol, and later on I never imagined that it would be a good paper, but somehow it became a good paper. And I went to Japan and presented that paper in ICC, International Conference on Communication. And what happened there, like, how do I know that the data that comes from that sensor, say, somebody can go and replace that sensor, say, for example, temperature, just make it 99 minus, right? The hot becomes cold, cold becomes hot. And that hot, cold, and whatever decisions you take at the server level, it becomes completely, I mean, a NOT gate is there. So, how do I do that? How do I know that the data that is coming from that sensor is actually the sensor which I have installed there? So, we use some kind of a zero knowledge protocol and all these things. So, some of these things, I mean, I can say that, look at the complications here. This is one diagram where you say that it's a small diagram. The black parts are actually critical parts. They have to be covered. The blue circles are the radius around which the sensor can sense. The red circles are the radius around which the sensor can communicate. So it's not that I can only sense. I should find another neighbor with whom I can communicate. So I have two problems here. One is that I need to communicate, I need to sense. So I should be with this, the area should be within the sensing range, and another node should be within my communication range. And what is the minimum number of sensors? What is the minimum sensing range? What is the minimum communication? And what are the multiple objectives so that we can do it? At the moment I expand it to 5,000 nodes, a 10 kilometer area or 100 kilometer area, the problem becomes almost untractable. We cannot solve the problem. So we did this work. How do I deploy them? How do I schedule them? And so that the deployment and scheduling taken together becomes an optimization problem. So what you did here, you take given any number of sensor nodes. I give m number of sensor nodes. You take n number of targets. You take an area, and then they have to be monitored. And I say that, look, every target has to be monitored by at least 2 nodes, because one node may fail. Somebody says no, not 2 nodes. Somebody says it is 3 nodes. Somebody says no, the targets can be not 2 or 3, but depending on the importance of the target, it can be a different. Target number 1 should be monitored by 10 sensors. Target number 2 can be monitored by 1. How do I do that? Then the problem becomes more complex. And then we try to solve it using some heuristics, some soft computing techniques and all these things. And we did that. A couple of papers in the process got published also. So we did it as a multi-objective optimization problem. We take 2 objectives, we take 3 objectives, we take 5 objectives at a time, and started working on it. Some students did actually really good work. Like, so when you take, say, these are all conflicting objectives, right? I want number of sensors to be minimum, because the deployment cost, tractability cost, and all these things will be minimum. I want communication radius should be less so that I don't consume more energy. I want sensing radius should be more so that maximum thing. But all these things cannot happen simultaneously. They are conflicting. And in case of conflicting, if I say that, look, I have 50 number of sensor nodes, and you find out what should be the sensing range, minimum sensing range, or sensing radius, and minimum communication radius, so that the entire area is covered and they are networked or they are connected. So these kind of problems need to be addressed, and many of my colleagues do that also. Alok does that. So Pujari does that to some extent also, like finding out where the hard problem lies and all these things. So some of these things I think I can, couple of these things I can miss. Localization is an issue, because I just want to tell you one particular problem here, like we faced here. Say we take distances, and if you look at C and D here in the left figure, C and D here, A, B here. All the distances are same. Even if I take distances to be accurate, even if I take the received signal strength indicator as estimation to my distance, and I say that they are fine, I can estimate the distance. Now look at this. If you change this, I mean, that's just a form. I mean, if you continuously form it. If I change this, everything, this is C and this is D. All distance are same, but location is different. The complete location is different. It's a very hard problem. Very, very few papers have come up, but still we attempted something. And the problem here, I think, Professor Murthy KPN came at the right time. I wanted him to pitch in and say that, look, I have seen a paper where people have used Monte Carlo method and other things, and what do you do with that? I mean, but they are not pretty good. They have used it just like that, generating random numbers and trying to do that. But can you do something here and try to test whether they are good or not good? Statistical distribution, people have used statistical distribution, people have used soft computing techniques. In fact, we have used soft computing techniques. People have used integer programming. They are very difficult to compute. I mean, it takes almost infinite amount of time. So we did all these things. This is another problem. Look at the splitting. C is here, D is here. Now, A, B. Everything, again, all the distance is same, but C came here, D came here. B, BC distance, BC distance, C. AC distance, C. BD, DD. You can put everything same, but still C is here and D is here, but your algorithm might give that C is there and D is here. So we need to talk about all these things actually. This is the work which you are saying that we use zero knowledge protocol for sensor security, finding out where the sensor lies, and the data that comes from that sensor is actually the sensor which I have deployed. Zero knowledge is basically, I mean, you can read it, but I give this example. It's one of my favorite examples. If somebody says that I know how to count the number of leaves in a tree, I say I know how to count the number of leaves. How to verify that? I will not tell you the technique. So I will not transfer the technique, but you have to satisfy yourself that I know how to count the number of leaves in a tree. So approach says that you take me to a tree, ask me to count. I'll give you some number, 29,937. You cannot count, you don't know how to count it. And then you blindfold me randomly, either you take out a leaf or don't take out a leaf. Open my blindfold, ask me to count again. If I know, I will tell. If I don't know, I will guess. Probability 50%, first distance. Repeat this experiment 10 times, 15 times, 20 times. Once caught, you are a thief. So that's how we look at this as a problem. In fact, because sensor networks keeps communicating other things, we generated this zero knowledge protocol, implemented this zero knowledge protocol in fact, and then, I mean, because nobody worked in that. Zero knowledge protocol was there for almost 5 or 6 decades, or maybe more than that. Sensor network is there, but somehow we could integrate these two and got a good result there. Soft sensing, I said that this is what we are working and we will be working. But this actually, it's very, very important to know how the sensor works. Because I cannot remove a physical sensor or a chemical sensor or a biological sensor without knowing how it works. So that working principle, if I can model mathematically, writing as an algorithm, probably I can remove some of them, not all of them. So, and then some of this data that comes need to be validated through the model actually. So if I understand how they are working, then I can also do that. And that's where probably some of my colleagues from other schools can help me out. This is something, I mean, I'm speaking to the gallery now. Oh, so this today is 14th February actually. So I didn't write Valentine's Day, but so it happens like, I mean, if you read this, this is possible. This is possible. This is doable, but it depends on how good you are in that particular task. so if you are good, your heartbeat is there, your perspiration is there, your movements are there, and you know you are in love. So and this actually blinks. So what I'm saying is that I have sensors, and if I have sensors, these are possible. But how do I make it possible? Heartbeat never says that to detect whether you are in love or not in love. But yes, if I can experiment it, write the algorithm, do it, and then this is possible. Finally, I want to conclude. This is what His Highness Dalai Lama said at some point of time in one of the talks. If anything I have said seems to be useful to you, I am happy. Otherwise, just forget it. But that's not the motto. This needs to be changed actually. If you don't find it interesting now, don't worry. Tomorrow you will be interested in it.